All right, let's dive right into this. I want you to imagine playing the ultimate high-stakes game of 3D Tetris. But in this version of the game, the blocks you're dropping weigh tens of thousands of tons. And getting that delicate balance between weight and volume just right, well, that dictates the difference between immense corporate profits or, worst-case scenario, catastrophic failure. That is the fascinating, high-pressure world of commercial ship cargo stowage. And our goal for this explainer is to break it all down for you, to be as detailed yet as simple as possible.
Because loading a colossal freighter goes so much further than just tossing boxes or pouring grain into a giant metal hold. It's honestly a masterclass in complex physics and economics, and it's governed by some pretty strict mathematical principles. So today, we're going to look exactly at how maritime professionals balance these incredible forces. How do they absolutely maximize their efficiency while keeping the crew and the vessel totally safe?
Here is our roadmap for today's explainer. We'll start with the high-stakes puzzle of the cargo hold itself. Then, we'll move into unlocking a critical metric known as the stowage factor. From there, we'll explore the physical realities of space and safety, compare weight versus volume, and finally, we're going to put on our shipping executive hats and calculate exactly how to maximize a vessel's revenue. Okay, Section 1, the high-stakes cargo puzzle.
Now, the rules on this list, these aren't just polite suggestions. They are the absolute, non-negotiable laws of the sea. The logistics are intense. For instance, cargo must be stowed portwise, meaning it has to be packed in the exact reverse order of the ports the ship is going to visit. Obviously, heavy packages go underneath lighter ones so nothing gets crushed. But critically, the load has to be distributed to achieve an even keel. That just means the ship sits perfectly level in the water, which lets it carry the maximum amount of cargo without running aground. Failing to respect these strict stability rules, well, that can result in massive financial penalties or literally the total loss of the ship.
Moving on to Section 2, unlocking the stowage factor.
Say hello to the stowage factor, or SF. This is the golden key that unlocks everything we're talking about today. The stowage factor is simply a number, and it tells us exactly how much volume, how much actual physical space, one single ton of a specific cargo is going to take up inside a ship's compartment. It makes sense when you think about it. The lighter and fluffier a commodity is, the more space 1 ton of it requires, which means its stowage factor is going to be a much higher number.
To keep this as detailed but as simple as possible, we really have to talk about units. Today, the stowage factor is officially expressed in cubic meters per metric ton. However, the global shipping market actually prefers to think in cubic feet. Why is that? Because the numbers are simply way easier to memorize during rapid-fire negotiations. So, professionals use this crucial conversion metric. 1 cubic meter equals precisely 35.3148 cubic feet.
But what if you aren't shipping solid boxes or grains? What about liquids like crude oil or chemicals? Well, for those, we throw stowage factor completely out the window and use specific gravity, or SG. Liquids naturally shape themselves to fill every single available millimeter of a compartment, so we just use a simple ratio compared to pure water. Crude oil, for example, is lighter than water, so its SG is less than 1.00. Solid cargo, on the other hand, has gaps, weird shapes, and packaging, and that is exactly why the stowage factor is so crucial for dry goods.
Let's look at Section 3, space, safety, and dunnage.
You see, relying on just the stowage factor alone isn't going to cut it, because a ship's hold is not a perfectly smooth box. Enter broken stowage. If you're a shipping executive, this is literally your least favorite term. It refers to all the unavoidable empty gaps lost between awkward cargo shapes, or the space eaten up by the ship's own internal steel pillars. This is totally non-earning space. It is quite literally air that pays zero freight dollars. And part of that broken stowage is actually eaten up by something called dunnage. Think of dunnage as the protective wrapping paper and scaffolding of the ship, usually made of timber, plastic, and heavy mats. Dunnage wedges the cargo into place so it doesn't violently shift around in ocean waves, but it does way more than just that. Imagine a ship loading steel in a hot tropical climate and then sailing to a freezing port. That temperature shift causes massive condensation, literally raining sweat down inside the hold. Dunnage keeps the cargo away from those dripping walls and creates ventilation to prevent catastrophic moisture damage.
Section 4, weight versus volume.
Understanding how different cargoes leave completely different footprints is absolutely foundational to maritime economics. Just look at the massive difference in the space required for 1 ton of material here. Iron ore concentrate is incredibly dense, boasting a tiny stowage factor of just 11 to 15. It takes up barely any room at all. But then consider copra, that's dried coconut meat used for oil. It is super light and bulky, requiring up to 110 cubic feet for that exact same single ton.
So, to make sense of this, the industry draws a hard line in the sand right at a stowage factor of 40. Anything under 40 is classified as a heavy cargo. With heavy cargo, the ship is going to hit its absolute maximum weight limit well before the physical hold is full, which leaves lots of empty space. Conversely, anything over a stowage factor of 40 is a light cargo. In this case, the ship fills up to the very top with physical volume, running out of room way before it ever reaches its maximum safe weight limit.
Which brings us to our final section. Section 5, maximizing the ship's revenue. Let's play a game. We are the operators of a massive commercial vessel, and we have a choice to make. We can load our ship with oats, which pays a really handsome $9 per ton. However, oats are bulky. They have a high stowage factor of 83. Alternatively, we can load manganese ore. Now that only pays $5 per ton, but it is incredibly dense with a stowage factor of just 18. At first glance, oats pay nearly double, but remember, they take up a ton of space. So which one is actually going to make us more money?
To solve this, we first have to figure out the absolute maximum weight our ship can legally carry today. This is based on how deep the port waters are, which is also known as the draft limit. We take our total allowed weight, which in this specific case is 37,154 metric tons. But wait, we can't fill all of that with just cargo. We have to subtract the heavy fuel, the fresh water, and the ship's provisions, which comes out to about 1,850 tons. That leaves us with our deadweight cargo capacity, or DWCC. Simply put, our ship can physically lift a maximum of 35,304 metric tons of cargo today.
And here is the absolute crux of our dilemma. Because manganese ore is so heavy and dense, we can easily load up to our absolute weight limit of 35,304 tons without running out of physical room inside the ship. But the oats? Totally different story. They are so fluffy and bulky that our cargo holds will be stuffed to the absolute ceiling when we hit just 20,957 tons. We literally just do not have the cubic volume to carry even one more grain of oats.
So let's run the final financial numbers. For the dense manganese ore, we multiply our mass of 35,304 loaded tons by that lower rate of $5. That nets us a total revenue of $176,520. Not bad. Now, for the oats, we could only fit 20,957 tons into our ship before running out of room, but they pay that premium $9 per ton rate. Does the high volume overcome the low weight? Any guesses?
And there it is. The oats generate $188,613. In this specific scenario, optimizing for volume and capturing the higher freight rate actually wins the game. It generates over $12,000 more in revenue, despite the ship carrying vastly less physical weight. It's just a stunning example of why understanding the deep mathematics of stowage factors is absolutely critical to maritime success.
Which leaves us with this final thought. We've just seen how a master puzzle of weight, space, broken stowage, and density governs the delivery of the goods that literally build our modern world. But it kind of makes you wonder, right? If the principles of volume versus weight dictate the fate of multi-million-dollar shipping empires, how might applying these exact same principles of efficiency change the way we organize our time, our resources, and the spaces we navigate in our own daily lives? Think about that the next time you pack in your own cargo. Thanks for joining me on this explainer.